That's his plan.
That's my plan.
I don't got the money for that.
I don't have the money for that, but you know what? It's 6 years versus 4 years. I'll give you 6 years. I like more money.
I already have one of my mom's buddies is one of my top engineers in the state, and he said that he'll let me finish something out of school. So I'm gonna go do that after 2 years out. Got to start with around the 16.
Really? Yeah, it's pretty standard.
Start around 6K, 7K.
It's pretty standard, like that
For
right now.
engineering, for engineering.
Or even if you go if you get through as union, you get to a union, that would be fantastic.
What kind of things like this? You guys seem like you got money.
It's still young. Literally that's it. And I don't mind it. My mom is in the shop. So I'm going down the street.
I'm trying to take care of other people.
I can't do
Oh, I'm fine with blood. It just possibly being around like 6 feet. I'm kind of looking for it to like a certain extent. The money I'm good with. It kind of just like fell into place. And then I'm after choose engineering school, and then working for a year or two, and try to go for architecture. Doing probably around 200 years of architecture course.
Oh, it's good that you guys have a plan. I'm all envious.
Kind of a plan to just do it together because what else am I gonna do? I love my current job. I make good money at my current job, but it's not something I want to create all my life.
No, definitely.
I mean, if I were to become like a job like that is like my boss, maybe. But I don't know. I'm not nearly as good as my notes is. That's kind of the plan for now. I don't see it changing anytime soon, because at least I don't want to spend more money in school. Why do you think I don't want to take any bill around? I'm saving up. Okay, I got 5K in the savings, in the locked deposit box. And then I got, between my savings, about 10 years. Top 10, in the nation. For a single engineering course, bro.
That's what I think.
That's what I'm doing right now, because I had opportunity to go and pay for a small portion of it, but it was not, a small portion was not worth it. Not worth it. Like how much we pay for schools in Aaron, it's like around like 3 times as much as, and you get less, like less one-on-one. So if your teacher needs help, you have a giant class of them. Not worth it. Like here, I don't have to pay for food, I don't have to pay for housing, I gotta pay my phone bill, I gotta pay for gas, and that's pretty good. So, honestly, high school was harder than high school. It's like, it wasn't as much work. Like that's what makes college hard, is the amount of work we did. So much more, but like the actual I mean, it didn't help that I was a track kid and a PE kid, so the majority of my free time was went towards those two. I don't know, it's like I took 40 I took a year of, it was so weird. They called it pre-cal class honors, but I still give it just college credits. Yeah. So I took 3 years worth of college math classes as well. So I entered with like 32 college credits, give or take. 24, sorry, 20 tests. So, and it was 30 as well. So, that also just taking medication with my mom for so it's my like time that was put like striking bands to work with the chemistry calculus. And calculus was like 3 hours a day. Calculus 1 is hard, like, calculus 1 is harder than calculus 2 because calculus 1 you're like, that's not calculus. And like, you do use a decent amount from your calc, but you're also learning a lot of the calculus on that. Calc 2 is it's more like, not physics based, but it has more science to it. You see that now?
Oh, yeah, I'm gonna
All right, let's get started. Happy Tuesday. Hope everybody enjoyed the long weekend. Let's do some announcements. I forgot to mention, I think it was on the syllabus, but I had basically a paper topic check-in. And so it's on Blackboard. And I think I said the due date as yesterday, but if you didn't do it, right, just do it kind of ASAP. I just want to know kind of where you're at, and this is also right for you to make sure that you've been thinking about your topic, what's going to be a good topic, and, you know, kind of honing in on exactly what you're going to write about. And I know many people have done this, but again, just keep working on that. And then I owe people some papers. I was having issues logging in. Probably just a server issue. So hopefully today I'll get those papers to y'all. And then keep asking me for papers if you need them. All right, so any other questions about anything? All right, so let's dive into our chapter. So now we're on chapter 13, kind of, and I feel like we're putting the pieces together now of what we did last week. So we'll get to our experiment later, maybe on a Thursday in lecture. And so now we just want to go over formally all these things about gases. And so of course, right, you probably know what a gas is, or at least have some basic understanding. Obviously, right, it's a phase of matter, and it's the phase of matter where, of course, particles are moving very randomly and rapidly. And of course, we can, again, think about steam and how that becomes a gas, right? We've all seen water in the three phases of matter, so obviously solid, liquid, gas. So, right, we're thinking about how our water boils out and moves out of its container. And so then we can kind of start with some assumptions here when we're thinking about how gas particles move. And this is considered our kinetic molecular theory. And this is kind of simplified for now, so we'll kind of talk about where it deviates. And so our first assumption is that our gas particles move in straight lines, of course, until they either collide with your container wall, right? If you're thinking about a balloon, it's going to collide with the inside of the balloon, or, right, it will bounce off another particle. And so we'll get back to this idea. And so basically, actually, I'll draw our balloon as we're thinking about this. Kind of what keeps our balloon inflated and what makes pressure. So obviously, right, maybe you breathe into your balloon, or you pump it up with some gas using an air pump. Maybe you're fancy and you use helium or something. And so what keeps it inflated and kind of what's going on is, of course, right, you have your gas inside and it's colliding with the inside walls of your balloon. And of course, it's working to keep it inflated, right, against atmospheric pressure. So obviously, your atmospheric pressure is beating back at the balloon. And so if it's inflated, right, you put enough moles in such that, right, it keeps it inflated against our atmosphere. And so now we can kind of think about, well, what really are those little collisions, right? So all those molecules are striking the inside of our container. And so those collisions lead to our pressure. So thinking about, well, what is pressure? And so pressure is just defined as the force exerted per unit area. Of course, right, in our case, by the gas molecules. You've probably seen this formula before. So pressure is just, again, force divided by our area, right? So now you're thinking about the surface area of the inside of the balloon. And so just some units. So pressure could be given in pascals here, so that's PA, and then that's just equal to 1 Newton over meter squared, or this kilogram over meter second squared. And so again, now we can think about what increases our pressure. So of course, our pressure of gas will depend on several factors. We'll quantify them as we go on, of course, but it'll be related to the number of gas particles. Again, right, you already can logic that, obviously, right? You keep blowing up your balloon, putting more gas in until it's as big as you want it. And then, of course, the pressure also depends on the volume. We could also compress our little balloon and make it have a higher pressure. And then we'll look at our speed, which is generally, right, related to temperature here. And so we can cool down the temperature, and then that gives us a lower average speed thanks to kinetic energy, right? Lower our kinetic energy. When we do the calculations, yes. So it goes back to being thermodynamically relevant. And so, yeah, we can kind of put that to remind us and get us in the correct mindset that, yeah, we'll be in Kelvin for those calculations. And so here are a few, again, assumptions we can discuss where the breakdown happens. And so when we're just kind of looking at our basic kinetic molecular theory, we're assuming that any collisions, either with each other or surfaces, are perfectly elastic. So that just means, right, no exchange of energy occurs. That also means, right, we're assuming that there's really no intermolecular forces between them, so we're not accounting for that right now. And of course, if we were to exchange energy, then those collisions would be inelastic. So that's one assumption. All right, so we'll look, like I said, we'll look at these factors, we'll quantify them, so this is just kind of repeating our factors. So, right, again, we'll be looking at how many moles in what volume, and then obviously, right, fewer gas particles. You can think about the lower force per unit area, right? You just have less molecules striking that particular area, and then that leads to lower pressure. And then obviously, right, a higher density of particles, just more collisions per that surface area, so higher pressure. And then again, we'll look at kind of this volume changing, what happens. We can also kind of start to understand, at least somewhat, weather patterns or basic weather effects. And so obviously, right, variations in pressure in the Earth's atmosphere create wind and all sorts of, right, bring storms. And so if you have an area of high pressure, right, that's a lot of, obviously, molecules in a certain region. And so if you have this high pressure system, then usually that clears out anything that you had there and usually brings clear weather. And then if you have some region, though, of low pressure, or you're left with low pressure, then that can lead to unstable weather, right? And that kind of makes sense. If you kind of have lower pressure, then things will want to come in to kind of equilibrate that. And so that can be associated with storms. And, right, your weatherman has something that looks like that, telling you where things are moving. Again, right, your high pressure can come in, clear out to low pressure, storms.
Is there a reason that one line is kind of dotted with red and blue and the other one's just straight blue?
Yeah, I'm not sure. And then we can also, of course, think about elevation and how that affects the number of gas particles. And so the number of gas particles in a given volume decreases with altitude. So, right, you have decreasing pressure at increasing altitude. And you're probably familiar with this. So sometimes, I don't know if you've heard the expression, right, like the air is thin. And so we can kind of, again, think about how this works in practice. And especially, right, if we think about Denver, Colorado, famous for being a mile-high city. And so sometimes, right, athletes will train in higher elevation because they want to have that thinner air where there's physically less oxygen, right? So their body has to become more efficient at processing oxygen, and so that can make you, right, a better athlete. That's also, right, considerations to take into, again, if you're training. I think here in the valley, we're pretty low. I don't remember if we're at sea level, but we're not too far above sea level. So again, right, if you want to think about competing with other athletes that always train at a higher elevation, right, you might have to go do some elevation training, get on Mount Ashland, right, get as much elevation training as you can. So that's the thought with that and how athletes kind of use that to their advantage as well.
People who grow up in higher elevations have a higher lung capacity.
Yeah. Yeah, and it goes back, like, you can go on a rabbit hole too about like the Sherpas, right, on Mount Everest, like all the local people, they're much more adapted, right, to climb, and so now it's a big tourism business, unfortunately, with the poor Sherpas doing all the work, and then the tourists just kind of at least taking themselves along, I think. But and then we can also think about, right, what happens when your ear pops, right? So maybe you've been on an airplane or even just driving around, right, in the mountains here, you can get enough elevation difference. And so, of course, what happens, there's a difference in pressure across the eardrum membrane. Then the membrane can be pushed out, and what we call a popped eardrum. And so, of course, right, they always say kind of chew gum or something to kind of help equilibrate your tubes there. So there's just our illustration of our reduced external pressure, again, right, from going maybe to a higher elevation, and then that bulges your eardrum. All right, so getting into now the math and how we measure stuff, and again, thinking kind of to our lab in some senses. And so this is one way to measure the pressure in this little barometer. And so we can, again, start to kind of see how our lab worked, or what the idea was. And so this is a little bit different from your lab setup, but we'll kind of explain the differences. And so in this case, right, we started with a vacuum tube, and then we have this pool of mercury here, and then atmospheric pressure, right, all the collisions of our air are beating down on our pool of mercury. And so it drives it up into our glass tube. And so now we understand where we get this measurement. So of course, if we were to measure it, this would be 760 millimeters of mercury. So that would be the height, or 29.92 inches of mercury. So depending what unit. And right, that's just a simple inches to millimeters conversion there. You saw that. And we don't generally use inches, but again, we saw it. So 1 inch equals 2.54 centimeters, just kind of reminding us where the heck everything is coming from. And then we have torr, which is just set basically as the same units, right? So we see down here that 760 millimeters of mercury is 1 ATM. Same with torr, so 760 torr is 1 ATM. So these can be used pretty interchangeably, you see that. And then we also, of course, see atmosphere, or ATM, and obviously our standard pressure is just 1 atmosphere. Then we have other units as well. So we mentioned the Pascal units. So we don't tend to see these as much. Actually, what we should throw in here are actually kilopascals. So you might see those, actually more than a Pascal. And so that would obviously be 101.325. So just the kilo version of pascals. And then your car probably uses this pounds per square inch unit. So 1 ATM is 14.7 PSI. And if I remember correctly, like a car tire, at least a typical small car, is around like 33 or so. 30, 33-ish PSI. So just over 2 ATM roughly. We have torr, like we mentioned, inches of mercury. And then we mentioned there's also bar. So that's another like weather unit, but scientists don't typically use bar too much. And 1.013 bars is an ATM. And then, of course, 1 atmosphere as our standard. All right, so let's just practice our simple conversion. And so now we have a cyclist that has this high performance road tire, and it has a pressure of 132 psi. So can you convert this to millimeters of mercury? Just take a few minutes to work on that. We'll go over it. So post your answer here in the chat. And I'll give people another minute or so to finish. All right, so what's our conversion factor here, right? What's our relationship between PSI and millimeters of mercury?
You divide by 14.7 in the ATM.
So we have, so let's just set up, so we have 14.7 PSI is equal to 760 millimeters of mercury. But then you told me we need to divide, so that looks good. So right, this is just our conversion factor. 14.7 PSI on bottom to cancel, times 760 millimeters of mercury. And then I have an answer in the chat. What do we get?
6824.49.
So 6, 8. And then I hear 2.4 or 2.6 in the chat. We have 3 sig figs. So we need a round anyways, so millimeters.
4897.
So 6, 8. So should I round it up to 3? Is that what you're telling me? So about 6,830 millimeters of mercury. So depending if you want to round this up or down, what you got. All right, not too bad there. Any questions on this one? So just our dimensional analysis again. All right, so now let's get into more of the calculations. And so we have, again, our 4 basic properties of gases that we're measuring. And so we have pressure. Our standard unit is an ATM. We'll kind of see when we need to use ATM, when we can use other units. Volume, and so again, standard unit is liters. Temperature, this one is always, always, always Kelvin, so just put a big fat star next to that one. So we always need to be in Kelvin. Again, like we mentioned, has to be thermodynamically relevant, tracing back to absolute zero. And then, just like we did in our lab, right, we can quantify our amount of moles from all this information. And so again, you kind of did the lab without really knowing this, but right, again, we'll piece through the lab, but right, basically that's what we did, or what y'all did, is you found the pressure, right, that your hydrogen was at. You measured your volume. Of course, you had your temperature. And then, right, you calculated your moles from that. And so then, why you were able to do that? Well, all these properties are interrelated. So if you change one, it affects the others. And so you can, again, solve for one of those. And so first, I feel like we'll do a little tease. So we'll look at the simple gas laws, and then we'll kind of put it all together with the combined gas laws. And so these simple gas laws are just investigating pairs of properties. And so these are the 3 kind of main ones. So we'll look at those. And so we'll start with Boyle's. So Boyle's is this volume pressure relationship. And basically, they have these little J tubes. And we can look at what kind of a J tube. And so basically what they had is they have a sample of trapped air, and then they would add mercury to it to increase the pressure. And so they essentially created a little piston. And so they observed an inverse relationship between volume and pressure. And so again, looking at this, so we can imagine they were using mercury. Again, in this case, we have a piston. So we double our weight. So we decrease our volume, obviously, with our piston. So volume goes to half according to this. And then our pressure, though, has to double, right, to account for that. And so now we have this inverse relationship. So our volume of a gas is inversely proportional to the pressure. And so, of course, right, decreasing the volume forces the molecules into a smaller space. And obviously, right, there'll be more collisions in a smaller space, increasing the pressure. And so what kind of happens though at these outer limits though, and what becomes an issue? It's kind of almost two issues in a way.
Can't condense the moment.
Whoa, what'd you say?
Can't condense the gas.
Or I guess like it will condense, right?
Well, yeah, to a certain point.
Yeah. So what you're getting at is it'll become a liquid, right? It's like what you're. I feel like
Yeah, I
that's.
guess. I mean, yeah.
Yeah. So right, you reach the compressibility limits is I think what you're trying to say, right? Is like basically we'll compress a gas and then it'll become a liquid, right? So such that it's not a gas. And then we also, of course, what's the other issue here with what limits how much we can compress our gas eventually? Just the volume of, right, our individual atoms of our gas. So of course, and we've kind of, again, we've oversimplified our gases, right? They're collisionless, elastic, and then we're assuming there's no interactions. But yes, we should remember that at some point, I just drew in little xenons, since those are large, right? You have your physical size of the atom, so you can only compress it so much. And like we mentioned, right, it'll be compressed to the point of a liquid. All right, so again, important part, we have this pressure times volume need to be constant. And then this gives us this relationship here. So that is, again, what's the important part. So this P1V1 is equal to P2V2. So whatever our first set of conditions are, we can find either a new pressure or volume based off of the change. And so kind of other things to think about and how to relate Boyle's law to real life. So does anybody do diving in here by any chance?
I have my certificate, but I've
That's cool. So then what do they tell you? And then Kate, have you dived or?
Not like professionally, but yeah.
But you've done it. So like what do they tell you right when you're coming up to the surface?
You have to go slowly or you get the bends, right?
Yeah, so you have to go slow. And then what does it mean to get the bends? So what's going on?
You have an increase in nitrogen in your bloodstream, and if you go up too quickly, then it boils out of your body essentially and causes you a lot of pain.
Yeah, so that's perfectly it, right? So let's think about that. So he gave us a good description. And so, okay, well, let's first think about the immense pressure that is going on in the water. So for roughly every 10 meters of depth, you get an additional 1 atmosphere of pressure roughly. And so if you were at 20 meters, then you would get about 3 atm of pressure. And so, right, like you were saying, so you have to think about all the gases that are dissolved in your blood. So of course, at such a low pressure, right now they're more compressed. And so, right, making the comment of the bends, well, what is the bends and what could happen? And so like our little scenario is walking us through. So of course, if we were to rise to the surface quickly, right, our pressure drops suddenly from, let's just say 3 to 1 atm. And so of course, if you're just holding your breath, that obviously, right, would hurt your lungs. It would be trying to explode out. But like he was saying, really what the danger is not just your lungs, right, and holding your breath, and it mentions this exhaling, but you have to give, right, that the gases time to re-expand in your blood, right, and then you have to process, exhale it out so that you don't have any issues, right, like getting little pop blood vessels in your eyes or brains or anything like that, which is what could happen. And I did have a student one year, it didn't happen to him, but he had seen it. He was in the military, so he had seen some like semi-horror story of a guy who rose a little bit too fast, and yeah, he had to like go to the hospital, and he felt kind of sick. And I think he was okay, but he did like, you know, pop some blood vessels somewhere or something, which right, always gets into what blood vessel are you going to pop where and how vital is that, which no one ever wants to gamble. What's also fascinating, if you ever want to go into another rabbit hole, is if you look into the people that do like competitive diving, you know, I don't know how they do it, because some of them go to like really incredible depths and rise back up, and I think some of them do get like damage from doing that, but I don't know if you also just like train your body. Hmm?
What kind of damage?
I mean, like brain damage and like, yeah. But that's like extreme. Like I'm talking about extreme people that go to like, you know, the limits of diving down just on one breath, and then you have to go back up like that. Those are extreme sports, but you have to think about like literally the physical limitations that they're starting to go up against. Anyways, back to our problems. So I'll rewrite our formula. And so as we breathe, other things to think about how we breathe. So you inhale by increasing your lung volume. So right, your diaphragm goes down so that literally, right, your lung volume increases. And so that means, right, your pressure drops. And so this kind of walks through that. So let's say we have an initial lung volume of 2.75 liters filled with air at atmospheric pressure of 1.02 atm. And so, right, let's just say you could capture that moment right before the air rushes in. So your lung volume is increased to 3.25 liters. And again, let's just say right before the air rushes in. So what would be the pressure in the lungs?
That'd be like 0.86 atmospheres.
That sounds a little off, but yeah, we'll give people another minute to finish. So then these we can just set up by identifying what's our initial conditions. So obviously V1, P1 here, and B2, so trying to solve for, again, P2 like it says here. And so now we can just plug it in to our formula here. And for these, as long as they're just comparative relationships, the units don't really matter as long as they match. It just so happened that we were in liters and ATMs, but we could have been in millimeters of mercury and milliliters, and that would have also worked. So then multiply these two, divide. So what do we get for x?
It's P2.
Yeah, so what's P2?
I got it, 0.86.
So 0.86 ATM, I see that in the chat. I think we need 3 sig figs, so 0.86, what do we get? 0.863 ATM there. And then, right, that sounds good, so it should be lower, and that makes sense, right, why air is now going to go in to fill in that lower pressure in our lungs there. Questions on that one? Okay, let's keep looking at these dual relationships. And so now we're looking at Charles's law. And so Charles's law is just looking at volume and temperature. And now they have a direct relationship. And so again, temperature is in Kelvin. And so now we're saying if the temperature increases, and then the other thing that we should note is, right, we're holding constant our pressure. And I forgot to mention, so it's on Blackboard. It's a link, and you might have seen these before. It's this website, these PhET simulations. But I put the link on there because they're pretty fun to play with if you haven't played with them. And so then you can just hit ideal. And so then we want to hold, let's see, I might have to give it some gas first. So I want to hold pressure constant. And then it will change the volume, it looks like. So then we can heat it up. And so right now we're seeing, okay, if we're heating it, and then it wants to keep our pressure constant, then it increases our volume. So let's do that again. So increase our heat. So you can see, right, our temperature rising, our pressure is being held constant. And then we can do the reverse. So of course we'll ice it back down. And then, right, volume decreasing to keep that pressure.
This is what people do in NASA.
And so then that gives us, right, our formula here. And I like rewriting it. So now we have V1 over T1. Again, temperature measured in kelvins, otherwise we'll get negative numbers, is equal to V2 over T2. And so again, right, our volume is proportional to our temperature. And so we could kind of see that in our simulation. So we'll look at other examples, but right, obviously we increase our kinetic energy, starts moving it more, but the caveat was, okay, if we want to hold our pressure constant, then we have to increase our volume. And then obviously, right, our greater volume spreads those collisions out, so our pressure was unchanged. And so again, now we have our graphical representation, so just showing this relationship. And so they all extrapolate back to absolute zero. And then of course, right, we have to mention that obviously we can't physically do this since all gases condense into liquids. So again, going back to those physical limitations of real gases, and we're kind of dancing around intermolecular forces too right now, so yeah.
Is there an upper limit to the kinetic energy that we gas can have? So like it eventually turns into plasma, but is there like a phase change the same way that there's in steam, water?
No, I don't think there's a phase change, because usually it'll like decompose at that point or burn or combust too. So those are other like limitations that you have to consider. And so you can do kind of a similar things, or you can impress, I guess I should say, your little kids with these types of experiments. And so instead of doing a PhET simulation, and I may do this on Thursday, I haven't decided. And so again, we can take a balloon, or sometimes maybe you've seen this with like a little can, like a aluminum can. And so if you take a balloon and of course put it in some ice water, you'll see it shrink. And then if you move it to a boiling water bath, again, right, you're not releasing any moles, and so then it would get bigger. So let's kind of look at this. I was like showing this video just because it's cool.
Are there any gases that you can condense into liquids at the temperature of ice water? Like, could you fill a balloon with a specific kind of gas and put it in like a tub of ice water and watch it turn into a liquid?
Yeah, I mean, it's just like, because you could probably do that with ether or pentane, you know, some low boiling organic. Yeah, let's watch. Where's my sound?
Hi everybody, I'm
There
meteorologist
we
Jay Birschbach along with Carl Nelson at the Imagination Station. Today we're dealing with one of my specialties, air pressure, the power of air pressure. And you may have seen this experiment before using a gas can or a smaller can. This is big scale. This is the Imagination Station's version of supersizing that experiment, showing air pressure which can crush this huge barrel. Carl.
So we got a steel 55-gallon drum here. I just want to give you a sense for how strong,
Okay.
how rugged these barrels are. Jay, if you could stabilize the barrel, I'm going to take a sledgehammer and try to... If you relied on me to crush this barrel, we'd be here all day.
Sure.
Because that thing is pretty tough. So instead, like you said, we're going to use air pressure to crush this drum. So
All
let me
right.
flip this up. I'm just going to stick it on its end here.
On its end? Oh, okay.
Because what I'm going to do first is add some water inside. About 6 cups of water. And what the water is going to do is we're going to create water vapor inside that we're going to heat up. Now water vapor when it's warmed up and air when it's warmed up occupy a little bit more space. Our goal is to try to trap some of that expanded air and water vapor inside. We're going to seal this up and then cool it down.
Okay.
We should see some crushing action at that point. But first, we're going to need to heat that air up.
Okay.
So help me flip this up on our stand here.
Okay.
The thing we're looking for, Jay, is we want to see a nice solid stream of steam coming out this opening here.
Sure.
And in order to do that, we can't just use like a blowtorch or anything small. As this is the supersized version, we're going to use one of these road torches.
Yeah, I think I'll back up.
Right. So it'll take a few seconds here to get the water warmed up inside the barrel, but to give you an idea how big the flame we're going to work with. There's a good sort of jet of steam shooting out, but we're going to try to capture that.
Okay.
By putting the plug back in. We're going to wrench it down tight because we don't want any of that warm, expanded air to escape. But the key now, Jay, is wheel over that tray of ice. We're going to cool this baby down really quick in a tray of ice. Hold on. And then just spin it down. Well, the first thing we should hear are a couple of ends of the drum popping in.
There we go.
The ends going in. There's the other end.
There we go.
Give it a second.
So what we're seeing is air pressure literally crush.
14.7 pounds per square inch of normal atmospheric pressure are now pushing down on this drum. And because that water vapor inside and that warm air inside
There it
has
goes.
cooled down, taking up less space, doing a lot more damage than that sledgehammer did earlier.
That is
to the drum.
amazing. Looks like a pop can or a soda can.
Looks like a pop can or a soda can. Or if you've ever rinsed out plastic milk jugs,
Sure.
and then you put the cap back on with warm water, stick it on the counter, you can see after a time they start to like collapse back in. Same principle, but it's a safe, at-home way you can do it.
Sure. Yeah, no one.
All right, so that was pretty fun. And so like they were saying, you could probably do this at home. I think you can do this with like a little aluminum soda can. And again, just kind of think about what they were doing and what the whole goal was. So obviously, right, they were using water because they wanted to condense it back down to a liquid, basically. So they, again, right, first they heated it up, kind of displacing all the other gas in there as well is kind of part of the idea, right? You just have it filled up with mainly water vapor in there. And that's what they were mentioning, right? They wanted to see steam. And so, right, it's kind of step 1, heat. Then step 2, cool back down. And obviously, right, they had it trapped. So now no more moles could go in. And so then that water, right, could have become a liquid again, leaving us with very little gas in there. Hence why it started, right, collapsing under the atmospheric pressure. That was pretty cool.
Are there any elements or molecules that have a higher gas to liquids expansion ratio than water?
I mean, I don't. Yeah, I mean, I feel like you're asking something that's not really quantified. So, and it still just depends on like boiling point. And you could use like, again, another liquid, but yeah, water is just obviously safer too. It has a higher specific heat. But. All right, let's try this last one before our break. So if we submerge a sample of gas, right, it has a volume of 2.8 liters at some temperature. Then we submerge the sample in ice water to 0 degrees Celsius. The volume is now 2.57 liters. So what is the initial temperature? And don't forget, right, you have to do the calculation in Kelvin and then convert. And I'll rewrite the formula just so you have it. So V1 over T1, V2 over T2. So what do we get? And you can first give me the answer in Kelvin. So I just showed the setup, right? Our initial conditions, we have an unknown T1, then our volume decrease. And I went ahead and used the 0.15 only because they gave us 0.00. Otherwise, normally I don't include that. So what do you get for T1? You have the answer, Bon?
Yes.
297.43 Kelvin. I also have the Celsius.
So 297.43 you said?
43.
And then what is that in Celsius?
24.43.
And so that sounds good, right? So just kind of sanity check yourself. So of course, right, if the volume was decreasing, then I expect the temperature initial to be a little higher, which it was, so it kind of makes sense. All right, that's a good spot for a 10-minute break. So yeah, come back around 12:02, and then we'll finish up.
I like your firefly shirt.
Thanks.
I haven't brought up my subjects yet, and I was trying to go into genetic engineering, so I wanted to know, like, what do you think would be like some good subjects and like, how long should it be? Like,
Well, the final paper is going to be like 5 pages. Yeah, I mean.
that should be 2 subjects.
Well, I was saying like either kind of 2 papers roughly where you like either can compare, contrast, or, I mean, it doesn't have to be just 2. You just kind of want to write on your
5
topic.
pages.
Yeah. I mean, I don't know if you want to talk about CRISPR. I just don't know if CRISPR is like too outside of chemistry, because that's like right in your technology. If you could get into like the chemical snipping of it, I think that'd be cool, like kind of how CRISPR works, like kind of what bonds are being broken, because we at least want to look at the chemistry of it, or like something like that, just like any other ways that they can genetically modify it, but like talk about the chemistry of it, like what exactly, like what bonds are being broken, like that could be cool.
That might be what I need.
Yeah, so just try to start diving into it, and then I can also help you look around.
And I've actually done this other case. Like I've
And there was
convinced
something else where it was like an armor that they made where it has like bonds
Oh, that's cool.
That we
that was pretty chemical.
Yeah, I mean, that would be a good topic too. But,
I'm really
yeah, it just
excited.
depends which way you want to go with
I
it.
got these brushes and this kit put watercolor paint in.
I like environmental science.
This looks like a small
Double majors or like.
Right? Watercolor is my
But I don't know if it's gonna like add more.
Yeah.
painting method.
Science.
Oh yeah, yeah.
Unless you know.
Really, yeah. I like it. I'm working on this. Do I have a picture of it? I'm working on this right now.
On Thursday,
That I'm really proud of.
But,
And then you have to spend
yes, I'm busy.
It's at Rock.
Oh, there's no secret.
So, but yeah, this is the. So I'm doing it. So I'm blocking down the like the value with color pencil and then going over it with the watercolors to do the texture. I'm so happy with how this turned out. It was so gorgeous.
Yeah, you did it in
It
the
looks like one of those ones where
I feel like it's all nice texture.
Right. Yeah.
It's gonna be great.
I like how I'm gonna
So jealous.
try to make it
I like my.
paper vibrant, and then this sword I'm just gonna
It's
do that. Yeah. So I'm really happy with how it's turning out. These wisteria trees.
We used to have the wisteria group at my house.
I know, I'm not sure.
You live in LA?
Yeah, I grew up.
I'm not sure.
Yeah, I grew up in my childhood was spent mainly in San Clemente, and then I lived in Riverside for high school. So I feel you.
People got mad at me. They like gave me like.
Yeah.
Yep. So glad I'm up here now. Right. I remember like when I moved up here, I was very similar. What are you like being very
They're like, I didn't expect you.
confident and very untrustworthy. I'm like, oh, it's so nice that like people like smile at you.
Well, they don't have like cards, but they like introduce us.
Definitely. It's so weird going back to like Sacramento, because my girlfriend was
I'm going to see you after you.
going to a coffee shop.
Oh, my
and
goodness.
it's like, they look at you like you're just so weird for coming to their coffee shop.
I experienced a lot of that. A lot of just kind of bitterness.
I
It's
don't
LA.
read into it too much, so I don't know any specifics, but.
I need to go grab some.
I know, really, still, just like, you know, did I think
How was your week?
it was good. I live a point where I got my own blind, so like I like in middle school. How about you?
That is so sad.
I know.
We do it homework, some work, and then we go home. I just do homework.
You getting this?
I'm getting this.
I feel like, people said that chemistry school can be really hard. But I feel like it's way easier to do. Thank you.
No. Jamie?
I want a question.
I'm scared.
See, we're getting there. We're getting there. Already? To one pair.
Is that right? Wait, okay, I either put one or two on fish I put
One pair or like two?
one pair.
One pair. Because I was, at first, I got one, and I had to redo it.
I did this exact same thing. I was like trying.
Not like an abstract, they just want like an introduction.
This is so nice.
It
What we
really
doing?
depends, like, where your paper.
We will.
Yeah.
I'll be walking up and
Going
go,
through these, and it's like, is it gonna go comparing trash, or you're just going through like reasons why
It's kind of, it used to be a high.
It gives me the hype, man. Especially when like if the class like joins early or something. That
More of an essay.
will feel bad.
More of an essay.
I mean, I'm
I mean, I don't know what you wanna classify it as an essay. I don't know what the relevance is.
Like me.
Yeah, I feel like it's hard to classify it. I feel like people using this taken out of context. Just like one thing. It's like a yeah thing. I think that only thing.
On the sidelines.
But it's like one thing, it's like what people are on, that's what's going on.
Right, it's just, so like each
Oh,
one.
no.
My dad said that.
Oh,
My
no.
dad said that. Well, yeah, my whole family is like, kids right now.
And sure,
I think.
it's just like, well, I like, older or younger?
Yeah, if you had like a triangle.
Oh, thank you.
Tricycle,
Like just and
Just.
yeah. Not that it's that much older.
When you told me, oh.
Don't say that though, because then you're making me feel like 20.
Yeah, I mean, so the way we want to count is, yeah, we want to count like the 3 different pylons, but I think what we're trying to get is like one delocalized pi system.
Yeah, I think that's always.
I'm ready to get turned.
Yeah, which, we'll kind of see in the lab a little,
Oh.
we'll identify like pi.
Oh, no.
Like, oh, there's
Be
a
careful.
there.
I'll be fine. It's just a bar.
It occurred to me I didn't turn the.
Yeah.
It's right there.
Okay, you guys stop doing that.
No. Can I have a glass of milk, please? Ice milk, please.
People think I'm a freak. Like, it's so, but I'm not drinking the bottle of milk.
I love it when it's like icy milk. And they like.
You need something.
Really try to.
Don't do it. You're good.
I skip anybody else with the quiz?
I'm on a cut right now. Like, you know, college deficit. I'm on a cut. But Trumbull is to call my name. So. Okay, if you try it, you have to play one. Don't be a big bad and get like 4 to 6.
All right, let's make our way back. All right, so let's do our last kind of pair, but then we'll put it all together. And so then our last one is, of course, volume and moles have a direct relationship. And I feel like this one is pretty self-explanatory. And so now we're saying, again, we're holding our pressure constant. And so now if we're going to add more moles, oops, so I went too crazy. But, right, obviously I already broke the machine. How do I reset this stupid thing? There we go. And so let's put more in there. And so again, we want to hold our pressure constant. We're going to change our volume. So that's what our Avogadro's law is saying. And so again, thinking about maybe blowing up a balloon. So now we're adding more particles in. Sorry, apparently I set the pressure too low, so I keep exploding it too easily. But right, we can see how it's decreasing. Let's, oh, that will take a long time for the particles to diffuse out. Okay, never mind. And so again, right, pretty self-explanatory that we have our direct relationship. So obviously more gas molecules equals a larger volume. Again, if we're holding pressure and temperature constant, which is always our assumption for these pairs. And, sorry? Yeah, Avogadro's law. So again, that's just our volume-mole relationship. And we'll get back to this, but essentially, equal volumes of gases contain equal number of molecules, so the identity does not matter. And so it's an equal relationship. So again, we're given this V1 over N1 is equal to V2 over N2. And so again, right, our volume is proportional to our number of gases. Obviously, if we increase our gas molecules, that increases our number of collisions. So like we saw with our little simulation that I kept blowing up, right, our volume must increase to account for those extra particles. All right, let's look at our problem. So I'll write our equation. So V1, N1, V2, N2. And so now we're given, so we have a male athlete in our research study. So it has a lung volume of 6.15 liters during deep inhalation and 0.254 moles of air. And so during exhalation, his lung volume decreases to 2.55. And then a little bit tricky, so the question is asking how many moles of gas does the athlete exhale? So think about what you need to do. Okay, so let's see what we did. So we can set up our problem. So obviously V1, N1, and we have V2 here. So we can set up our problem. So 6.15 liters is proportional to 0.254 moles. And so we have 2.55 liters. And so notice what we're calculating first, right? So we need to calculate, well, how much is remaining? Yeah, so what do we get for moles of gas remaining? So 0.15. Sorry, 0.105 moles remaining. And so then did the subtraction. So I don't have my calculator out. So this is remaining in lung. And so then, right, just do the subtraction. So 0.254 minus what was in the lungs. And so then, did we get 0.149 moles exhaled? And so I saw that in the chat. So then 0.149 moles exhaled. So good job with that one. Any questions? All right, so let's put it all together now. And we have our, what's called our ideal gas law now. And so this is what we were given on our paper, or not on our lab, excuse me. And so kind of, right, the beauty now of this ideal gas law is it combines all these variables right into one relationship. And so now this is where units do matter. So we have PV equals nRT. So this is where pressure has to be in ATM, volume has to be in liters, N is in moles, and R is our ideal gas constant. This one is rounded in your lab manual. You had 0.08206. It's fine to use 0.0821. And temperature is in Kelvin. And so let's talk about a few things. So gas law. So if you were to just Google gas constant, say you forgot, you would get a bunch of different answers. And so let's kind of look at that and understand where it's coming from. So this is why the units matter. And so depending on what we do, so we'll look at other calculations with R, where we are looking at joules and Kelvin and moles, and we might use this 8.314, but that's not what we're doing. And then you can see, right, there's a bunch of other variations of this gas constant depending on what units you're in. So just be aware of that. So I just want you to be aware of, okay, all these exist, right, again, depending on different units. And now we can find the one that we're familiar with. So this 0.082, then obviously gives us a much more precise value. And okay, there we're back, liters, ATMs, Kelvin, moles. So that shows us, again, where our gas constant came from. So again, if you switch units, different gas constant, but that just, again, tells you what units we need to be in. So let's look at our, what I call our little baby derivation. Because the other nice thing about this ideal gas law, of course, is that we can derive these other three laws that we just looked at. And so let's go through that. And so, right, we just said, well, we have PV equals nRT, where R was a constant, was our gas constant. And so that means that we can rearrange our equation to set up P times V over RT, over NT equals R, because again, R is just our constant. And then we can set another relationship. So, right, we can have any other set of conditions of P2, V2 over N2, T2. And so then you can see where this is going. So now we have kind of our new relationship. So P1, V1 over N1, T1 is equal to P2, V2 over N2, T2. And so this is just, right, another form of our combined gas law. And then we can see how we can rederive all our other laws by holding, again, right, these variables constant. So if we go back to Boyle's, so we said N and T were constant. And so let's, again, kind of rederive this. So Boyle's, we had N and T were constant. And so if they're constant, right, if they're not changed in the problem, then we know we can just eliminate them. And so yes, right, that leaves us back with P1, V1 equals P2, V2, or any other scenario. And so sometimes, right, you can change 3 variables, 4 variables, as long as you have, right, your initial and final conditions of enough of those. So you could change, right, pressure, volume, temperature, maybe hold moles constant. It just depends on the problem. So then I would kind of, right, maybe circle this, highlight this. This is all you need. And then, right, kind of star this. Remember how to derive this. But this is our combined gas laws that, again, helps us. And so that's all that's being emphasized here is, again, just rederiving all these laws out. So Charles, right, was moles and pressure were held constant. So we can get back out our volume, temperature. And then Avogadro, we held pressure and temperature constant. Other things to think about is, again, the kind of relationships between them. Oops. And so what I mean by that, so let's rewrite this. So PV equals nRT. And so notice, so what happens when the variables are on the same side? Or what do you remember about this pressure-volume relationship? What do we say?
It remains constant.
So yeah, pressure times volume is constant, but then were they directly, indirectly?
They're directly proportional.
But they're indirectly, right? Because if one goes up, the other goes down. Or inversely, sorry, we should say inversely related is a better term. So they're inversely related. And so what we want to recognize, and so let's look at what do we remember about volume and temperature. What kind of a relationship was that? So direct, right? And they are on opposite sides. And so now you can use that logic for anything. So if it's on the same side, so again, now we can look at moles and temperature. They're going to be inversely related. Right, so again, if you wanted to hold pressure and volume constant, obviously as you increase the number of moles, you would have to decrease the temperature so that this would be constant. And then again, anything else is direct, so that's going to be volume and moles, which we saw, right? That was Avogadro's. Pressure and temperature, right, would be directly related. So just remember that. So directly related, they're going to be on opposite sides here of the equation. And inversely related, right, same side.
How was the value for R derived?
Oh, well, R is a constant.
Yeah, how was it discovered?
Oh, I mean, it would be based off of the other values that you could like rederive it from. Because, right, you could go PV over NT equals R.
Oh, I see.
So then, yeah, initially, that's how you could calculate it.
Yeah, that makes sense.
And so then this is trying to hint at, again, what I was saying, but again, you can change all four variables is the power of our formula here, right? We can change all four variables and you can still solve it with our math. And so, right, it says blah, blah, blah. We can find our other gas laws just like we did. Or we can, right, find one of our variables if we know the other three. So lots of different ways we can do this, right? So then mathematically on a question, you're asking yourselves, are we doing kind of a before and after scenario where we're changing variables, or are we trying to solve for something, right? Maybe we have pressure, volume, temperature, and we just need to get moles, right? Like just like we did in lab. So let's see what it wants us to do. So calculate the volume occupied by 0.845 moles of nitrogen gas at 1.37 atm and our temperature of 315. So again, just think about what formula you need to use. So how's this problem going? What formula did we use?
I got P over NTR equals V.
So PV equals nRT, and then you rearranged it to solve for volume.
Yeah, P over nRT equals e to the negative 1 for 1 over V. Yeah, you divide by V and then divide by nRT. You get P over nRT equals 1 over V.
I feel like,
You told me that.
yeah. All right, so then doing that, and then, so n 0.845 times r, so 0.0821, or you could use a more precise value, times 315, divided by our pressure. So about 15.95 liters for our volume. Did we all get that? Yes, no? One yes. Chat's pretty quiet, don't know. And so about 3 sig figs, so we can round up, so we might have to round up to 16, since that boosts it, so about 16.0 liters there for our volume.
I got 27 liters.
I got 16.
So yeah, I would double check your numbers. I think people are getting 16. Questions?
So is the constant, we're just saying that it equals 3.0821?
Yeah, that's sufficient. I mean, you know, if you really want to get picky about it, it depends on the sig figs. You know, here we do have only 3 sig figs, so yeah, it's only necessary to do the 3. You know, you could argue that if our problem were more precise, maybe we want to use a better value, but I probably won't be that picky.
But I used the wrong variable. I used pressure instead of volume.
Right. And so now let's look at how this kind of relates. So now we have what's called our standard conditions. And these are just known as STP. So we might see this in like a problem. And so STP is considered 1 ATM and then kind of different 0 degrees Celsius. So just make sure you're set at 0 or 273 Kelvin. And then our standard amount is 1 mole. And then, of course, if we were to plug this in to PV equals nRT, we would calculate that our standard volume is 22.4 liters. And so this is pretty important, right? So then we can say, okay, at STP, right, 1 mole of any gas is 22.4 liters. So this will help us later with problem solving and proportions under these STP conditions. And so here they just run through the calculation, and so you can punch it into your calculator if you want to be convinced. But yes, right, we'll get our 22.4 liters. And so other relationships to think about is, again, okay, if we have our molar volume, again, we said we had 1 mole of gas at STP. So that means that we have, right, 6.022 times 10 to the 23rd molecules. And yeah, right, Avogadro number as always, just keeping in mind those conversion factors and those relationships. Because then you can get, oh, at STP, we have, right, 6.022 times 10 to the 23rd molecules.
That takes up 22.4 liters.
Yep. And so it does mention, of course, they have different masses, so right, their densities would be considered different, but they all have the same volume, or at least we're assuming with our kinetic molecular theory, yeah.
Like normally be like a gram per. Okay, that would be like 20 times. Never mind.
Yeah, well, it's still, so then you could take, right, your molar amount, so helium has a molecular weight of 4 grams for its molar weight.
Yeah.
So yeah, 4 divided by 22.4, so yeah, different densities, but still 1 mole.
I want to be the same as like the volume is 22.4, then the number is.
Yeah, but so then, right, density though is mass over volume. So yeah, volume's always the same, but then, right, these masses, so you'll have 4 grams versus, I don't know what xenon is, 100 and something. So 131 grams, right, per 22.4 liters. So, right, different densities. And then this would be, right, like 16 roughly. All right, questions about that? Makes sense. All right, so more kind of mathy things and things to think about.
I have one question, actually.
Oh, yeah.
Do the properties of the gases change at all for radioactive gases? Or is it the same?
Yeah, it doesn't really change. I mean, again, we'll talk about the same effects of like mass effects. So, right, you could obviously have slightly different rates of leakage, which we'll again get into. But all right, and so let's again think about our atmosphere. And so many gas samples are not pure, but mixtures of gases. And so, for example, the air that we breathe is, of course, actually mainly nitrogen. And so we can say that it's 78% nitrogen, 21% oxygen, and then 0.9% argon. And then we get into 0.04% carbon dioxide. And of course, right, other trace gases that are not listed. So xenon, methane, et cetera, and so in certain applications, so again, kind of going back to, we don't care about the identity of the gas, we can treat it as just one mixture. And so again, even though it's a mixture, our pressure, volume, temperature can be treated like we have one substance. We're just looking at the total moles, so total N, I'll abbreviate. And so by knowing our pressure, volume, and temperature, our total moles can still be determined. And again, we'll look at how these percentages lead to our partial pressures. And so then we get into Dalton's law here. And again, right in the back of your mind, you're thinking PV equals nRT here. And so it states that the total pressure of a gas mixture is the sum of the partial pressures. And so again, right, we're assuming that the particles have negligible size. They do not interact. So obviously, right, there's going to be some deviations from this ideal that we're working with, but it doesn't actually deviate too much. And again, other things to keep in mind. So particles of different masses have the same average kinetic energy. And so we can, again, break down our pressure of our gases in a mixture to our partial pressure. And our partial pressure is either related to the fraction, so right, just like we had the percentages of, let's say, our gas mixture, or of course, we can figure out our mole ratio. And so the sum of all our partial pressures is equal to our total pressure. Again, gases behave independently. Yeah, a lot of sirens today.
So like a fire again, like the other day.
Yeah, hopefully there's no buildings on fire.
It was crazy. It was like I walked out of school when that happened. And it was like the first thing I saw is just all that stuff. It was the mattress square. Oh no, you're talking about the. No, the yeah.
Yeah, anyways. So then we have, again, our pressure due to any individual gas component is our partial pressure. And so again, PV equals nRT. So like we were saying, we can figure out our pressure from, right, our number of moles, and we can figure that out proportionally. Oh, I think they pulled it out to like try to highlight that they're more related, but yeah, it's the same thing as it being on top. And so again, right, it's trying to highlight that it's additive. So that's really what it's getting at, right? That your moles are additive, because again, we said the identity doesn't matter of our gas. So then we can get our sum of our pressures, again, equals our total pressure, because PV equals nRT. So we can get our mole fractions and add those up. Yeah.
Would this effectively be like a mixture of gases inside a container?
Yeah, so it could be either in a container or again, like the air we breathe. So we'll go back and quantify our partial pressures of everything in our air. And so again, we've kind of stated this, so our pressure total is equal to the sum of everything. And so now we can put some numbers to it. So, okay, our partial pressure then of our component is its mole fraction multiplied by the total pressure. And so, right, we were given that nitrogen has a 78% composition of air. And so that's going to be 78% fraction of the total pressure. And so assuming, right, we're just at 1 atm for our air, that means our nitrogen pressure is contributing 0.78 atm. And then we can add up, right, the other components. So this just roughly accounts for the three major gases. But then we have, so 0.78 atm times, and then if you don't remember, I'll just go back and show you. So, right, we said oxygen was 21%, and then they rounded argon right to roughly 1%. And so that gives us our plus 0.21 atm plus our about 0.01 atm for argon, and then obviously smaller for the other trace gas mixtures. So does that make sense? Now let's try it.
Do denser gases exert more pressure?
So in this case, right, we're assuming they're all the same. So that's, and so a 1 liter mixture of helium, neon, and argon has a total pressure of 662 millimeters at 298 Kelvin. So if our helium is 341 millimeters of mercury and our neon is 112 millimeters of mercury, so what mass of argon is present? So how far did we get in this one? I see like some kind of partial answers. So what's kind of the first thing that you had to do with this?
The first thing I did was identify the unknown variable, which is n. Before you do that, I guess you have to take the total pressure, subtract the pressure of helium and neon from the total, and that gives you 209 milliliters of mercury. Once you have that,
Sorry, what'd you get?
209.
209, sorry.
Yes.
I just didn't hear you.
And once you have that, you can find that the temperature, the pressure, and the volume are all defined, and then R is already a constant. So if you rearrange the PV equals nRT equation, so that becomes PV over RT equals N,
Yep.
and that's it.
So that looks good,
And
and
you have to
then,
find the molar mass of argon.
and so right, you have to convert this to ATM, which I'm seeing in the chat is 0.275, so just dividing right by 760. And so this looks good. Right, volume is still 1 liter. Equals, so N, so trying to solve for N. And then T. And so what do we get for N then? Punch it in, let's see. So 0.275 divided by our temperature.
Should be like 11 milliliters. 0.11.
Or, but this is moles, right?
Right.
So 0.0112 moles. And I see that in the chat. And then, yeah, you mentioned that we had to get the molecular weight of argon. Can somebody help me with that? I forgot it. Argon.
39.948.
49?
39.
Oh, 39. Jeez. 39.948?
Yeah.
Okay. And so that's grams per mole. And so right now we just need to multiply those. So times our molecular weight. Oops. And so it gives us about 0.45 or so grams. We can keep the 3 sig figs, so 0.449 grams of argon. Excellent. Questions on that one? I was just putting the pieces together. So again, right, main things to think about, we have our PV equals nRT formula. Now we have, if I can find it, right, our P1 V1 equals over N1 T1 equals P2 V2 over N2 T2. So those are like your main formulas, and then everything else is just kind of problem solving. So we'll probably just stop there before we get into it, but we'll start off on Thursday, of course, kind of comparing this setup, right, versus the setup that we did in our experiment and kind of where we got all those numbers from. All right, I will see y'all in lab then We have a fun TLC lab, kind of getting into organic chemistry a little bit. So that'll be good foundation for OCHEM. All right, I'll keep the stream running another minute or two. Just let me know if there are any questions. Otherwise, I'll see y'all in lab. Yeah, homework. Make sure your name's on it.
Yeah.